Today's program, part of our ongoing program related to space, is titled Humans in Space, Adapting to the Final Frontier, and it's presented by Mallika Sarma. Mallika holds a BS in Psychology and Evolutionary Anthropology from the University of Michigan and is currently a Ph.D. candidate in anthropology with an emphasis in human biology. Working in the Hormones, Health, and Human Behavior Lab, her research focuses on human development, plasticity, niche construction, and behavioral acclimation and adaptation to extreme environments. Specifically, high-altitude environments and analog environments for long-duration space travel and extraterrestrial habitation. Mallika is currently NSF Graduate Research Fellow and also holds the Notre Dame Dean's Fellowship. Please welcome Mallika Sarma.
Hello? Okay. Hi, everyone. Thank you so much for having me here today. So I want to start with an exercise. Everyone go ahead and close your eyes and imagine we are in the future. It is the year 2035, and we have humans on Mars. Now, over the past several decades, we have orbited the planet, we have put rovers on the surface, we've taken pictures of landscape and sediment, but this is different. We have boots on the ground, actual humans on another planet. Now, under these extreme conditions, do we know what's happening to their body? And how are they acclimating and adapting? And how do we make sure that they don't die? You can go ahead and open your eyes. So we know that here on Earth, humans have successfully survived for extended periods of times, over generations, in a whole range of environments and ecosystems. So from high altitude environments to desert environments to extreme cold, like in circumpolar regions, and even in resource abundant environments, but with high parasitic and pathogenic loads. But we really know nothing about what might happen in an extraterrestrial environment. And we want to know specifically what could happen on the way there. What would happen in a long-duration mission? Now, places like NASA are thinking about this very deeply. These are things that we need to find out. And so they have identified 5 defining impacting factors that we should be concerned about. The first is changes in gravity fields. We know that gravity is going to be extremely different whether you're in space or on a different planet or even the moon. We know that these things affect spatial orientation, hand-eye coordination, balance, locomotion, bone loss, muscle loss, etc. The next is isolation and confinement. When you are on a long-duration mission, if you're on an extended habitation stay, you're by yourself and you're stuck with the same people that you will be for the entire mission. We know that that's related to a decline in mood, in cognition, morale, or interpersonal interaction. But also physiologically, there are changes in circadian rhythm dysfunction and nutritional deficiency. The third item that they're concerned about is a hostile enclosed environment. So it's a little bit different from this isolation and confinement, where the environment itself is you're basically trapped in a tin can. When they talk about the early Apollo missions, they say you're taking a bunch of astronauts, you're putting them in a tin can, and you're sending them up to the moon. Now, the fact that they're actually in one contained space is something to actually be concerned about. There is the easy transference of microbes and microorganisms from person to person, and also stress hormone elevation and immune system alteration. Probably the most dramatic thing that individuals are concerned about is space radiation. On a long-duration mission, you can expect to encounter over 10 times the radiation experienced on Earth. There are damaged central nervous system implications, altered cognitive function, reduced motor function, changed behavioral systems, all things that are extremely important when you're thinking of overall performance. And the last is distance from Earth. Some of the things that come from that include communication delays. So if someone gets sick, if they get a kidney stone, how long will it take to actually get in touch with a doctor? As well as limited to no opportunities for reply. So if you have a medical emergency, you might send a message out and may never ever get back, so you are responsible for your own health and well-being of your crew. Now, the way that NASA is kind of looking at these human problems is this very, very complicated map. I'm not even going to attempt to try and zoom in. There's a lot of words, a lot of things happening. I think from this image, it's very clear to see that NASA is an engineering organization, and so they approach it from a very engineering perspective. But I'll try and break down some of the things. So first you have these red bars. These are the most important things we need to deal with as soon as possible. If we don't deal with it, our astronauts are going to die, and we're not going to have successful missions. Some things like this include space radiation exposure and its risks to cancer, as well as long-term medication storage. These are things we need to solve as soon as possible. They are absolutely integral to the success of a mission. Now, the yellow is, okay, these are things that we probably should figure out sooner rather than later, and that would be something like decompression sickness. Now, you have these lovely gray bars at the bottom, which are things that we basically have no idea what is even going to happen. We have totally inadequate data. So something like celestial dust exposure. We have absolutely no idea how that's going to impact the human body and how much that might impact a mission. Now, this all might seem extremely overwhelming, but luckily, we are not starting from scratch. So there are two things that we need to consider. First, we have that earlier slide, humans adapting to a whole series of environments. Now, humans, as a species, have a long history of flexibly acclimating and adapting to a wide range of environments. Now, true, most of these have been on Earth with our very basics that we all need, including water, sunlight, etc. But what has made humans extremely successful as a species is our plasticity and ability to adjust to the environment around us. Now, the second thing that we need to consider is that in any environment that sustains long-term adaptations, we never see just one single individual adapting alone. Even in instances of mountain climbing, you see people summiting Mount Everest, it's usually never just one individual. You have a team, you have a group of people. Now, an individual human is nested within a larger group of individuals. And for a species as highly cooperative and social as humans, it's integral that we remember this. We can never just look at one individual's physiology without considering the larger context, including the larger social context that they're in. Okay, so now I'm going to jump a little bit to my research, my dissertation research, and what exactly I'm looking at. Now, it's extremely hard to answer these very big NASA-driven questions or any space agency-driven questions about the human body and physiology when we're still solving engineering problems. We're still trying to figure out how do we have rockets that can last long enough? How do we have enough storage space? How do we carry air? How do we recycle all of our urine and fecal matter? But we need to answer these human questions because that's what's going to determine if we have a successful human spaceflight mission. Now, the answer of looking at that is looking at humans here on Earth and seeing what we can figure out. So my research generally looks at how do humans survive and thrive in novel, challenging, and extreme environments. And specifically, I'm looking at individual physiology and behavior and the roles that social and group dynamics play on individual physiology. Okay, so the way that I'm looking at this is considering 4 factors. Hormones, I can use my pointer here, energy expenditure, social and group dynamics, and this overall general physical and mental health and well-being. Now, the relationship between these 4 factors is extremely complex. You could write several dissertations on just the relationship on these 4 factors. But I do want to do a really quick overview of why we're even bothering to look at these. Of all the physiological systems, of all of the behavioral systems, why these 4 things in particular? Okay, so the hormones that I'm looking at specifically are cortisol and testosterone. So just a show of hands, who here has heard of cortisol? Okay, that's what I thought. It's a pretty popular hormone. Now, who here has heard of testosterone? Okay, yes. So if anyone goes to the gym, if you get ads for like bodybuilding supplements, you've definitely heard of testosterone. Now, testosterone and cortisol are both metabolic hormones as well as having important behavioral factors. Now, there's a bidirectional relationship between the hormonal systems, both cortisol and testosterone are part of these larger hormonal systems, and energy expenditure. So both of these hormones play an important role in determining how energy is allocated. So very simply, they're messengers that are telling the body what parts need energy. So let's give an example. You're walking through the woods, having a grand old time, and you run into a bear. Now, as someone who has done a lot of wilderness research, you 100% do not run from the bear. That is bad. Don't do that. But what happens is your body has a fight or flight response. That is your sympathetic nervous system. You have that upshoot of adrenaline. The bear is right there. It's like, okay, what am I going to do? So in this case, you probably want to scare the bear away, try and make a lot of noise. But what happens after your adrenaline rush? The next thing that is released is an increase in cortisol, because cortisol is telling your body, okay, something is about to happen, do something, let's increase that cortisol. Cortisol is telling your body, okay, let's release some sugars, we'll get ready to fight this bear. Now, when you're about to fight a bear, you don't need to be worrying about things like reproduction. So, testosterone is produced by the gonads, you don't need to be reproducing right now, so that is all going to be tamped down. So that's just an example of how hormones are used to allocate energy. Now, how you spend energy is in a feedback loop to overall hormone production. Thus, you have this bidirectional relationship. This is always in a feedback loop with itself. Now, hormones are also extremely sensitive to social and group dynamics, and this too is bidirectional. So where hormones are shaping social behavior and then overall dynamics are then impacting individual hormone levels. Now, cortisol, as I'm sure most of you know, is a stress hormone. It is considered to be the stress hormone. And in a species that's as highly cooperative and social as us, something that was specifically for a fight or flight response has been co-opted in our own brains to respond to social stresses such as status threat or feelings of isolation. So if you are someone who's extremely afraid of public speaking, or you're someone who sees your crush in front of you and you want to speak to them, the feelings that you get, that extreme adrenaline and then that stress that you're feeling after is actually the same response that would happen if you saw a bear in the woods. Now, testosterone, the reason why we see it on all of these gym ads, we see it on all these supplements, is because it's also important physiologically to the development of musculature and bone mass. But it's also highly reactive to cooperative and competitive behaviors. So things about aggression, that's when you see a lot of instances of testosterone research. Now, to make things even more complicated, these are related, but social and group dynamics and energy expenditure are also related. So think about if you are requiring someone to help you with a task. If you are with a group of friends, you are going on a hike, someone is helping you, I will carry your pack, I will help you set up camp. You then have to spend less energy. But physiologically, we could consider that these hormones right here might moderate the relationship between these group dynamics and overall energy expenditure. Now, together, all of these things together impact physical and mental health and well-being and overall performance. Okay, so a little bit now about the actual work that I did. For my dissertation work, I worked with the National Outdoor Leadership School. Is anyone here familiar with that? Is anyone here familiar with Outward Bound? Yeah? Okay, so Knowles National Outdoor Leadership School is very, very similar to that. So it's a leadership school. They teach wilderness and leadership skills. And I was working with individuals that were going on 90-day expeditions through the American West. So if we are thinking about analogs that we can use for space missions, this is probably as close as we can get. So some of the stressors that they faced, first they had high altitude and cold stress. Now, these are very, very well-documented stressors that impact the human physiology in long-term ways. And if anyone has any questions later, we can talk about that some more. But if we're thinking about specific to space missions, what are some of the other stressors that they're facing? One is experiencing a novel environment. There's a whole bunch of changes that happen when you walk into a new environment for the first time. If anyone has started a new job, started a new school, if you've gone camping and you've never gone camping before. Your body is reacting in a very specific way. Next, you have your fixed nutritional availability. Students are taking all of the materials that they need out with them. They're taking all of the food, they are carrying it themselves. Once they run out of it, they can't stop by Target and get more food. Next, we have the constrained access to resources. Now, this is both an actual legitimate pragmatic issue, but also a psychological issue. So you can only have, again, the resources that you can travel with you, but you also know I'm in the middle of nowhere. If I need resources, I can't get them. I have to figure it out myself. Now, what I think is probably the most interesting is that it is a new social group. The students that they're with through the duration of their expedition are people that they've usually never met before. I think that there may have been one or two exceptions to that, but for the most part, they've never met the people that they're with before. And I wanted to ask, how do the social dynamics, so they're on this expedition, the group dynamics of their expedition, influence how individuals are acclimating to their environments and spending energy? Again, energy becomes this key metric that we're looking at in an extreme and novel environment. Okay, so what are the ways that we're collecting this data? We have these big questions, but what is the actual tangible data that we have to work with? So for energy, we were looking at first anthropometrics. This is just basic body changes. We were able to measure students as they were throughout the entire expeditions, looking at changes in weight, body fat, and lean muscle mass. We also hooked them up to little actigraph monitors, which are just very fancy Fitbits. You can see the big red honking pieces. You put them on your wrist right there. And they have these matching Bluetooth-connected heart rate monitors. So they're wearing that. We're able to see their movement and get an estimate about energy expenditure and how much activity that they're doing. Now, hormones, back to that question about how is energy being allocated. So the ways that we were collecting that was looking at saliva samples, so just having people spit in a tube, and collecting fingernails, because with fingernails you're able to get samples about 3 months worth of data. And then looking at interpersonal social dynamics. Now, they're on these expeditions. Unfortunately, we can't have a drone following them along or having a mole on their expedition keeping track of everything that they're doing. But what we can do is have them fill out questionnaires answering exactly how they are relating to people on their group, free listing who they feel is the most cooperative, who is the least cooperative, etc. And we did collect some additional data. We have some dried blood spots to look at immune system factors, overall wilderness conditions. Did they experience an avalanche? That is probably a big condition impacting their stress physiology, as well as informal interviews, how they felt about the entire course itself. Now, this is my dissertation work, so I'm able to present some of my preliminary findings. I'm hoping that in the next couple of months, I will have more findings to share. But specifically looking at the social dynamics and overall energy expenditure physiology, what we're finding is first looking at social support from home. Okay, let me explain this graph a little bit. So here we have perceived social support. So this is a scale from 30 to 80, and we're asking everyone, before you even start the course, how much support are you getting from home? How much support are you getting from your friends, from your family? Not involving anyone on the course itself, but how much support are you starting off with? And then we're looking at energy expenditure. So the average kilocalories someone is spending per hour. How much effort are you really putting in any hour? And so what we're finding, it's quite interesting, is that the more social support that people are coming in with from home means they are spending less energy overall. So they're working less. They don't have to work as hard. They're more conservative with their energy expenditure if they have more social support from home. Okay, it's a new day though, blank slate. We don't care about what's happening from you at home. What we want to know is what's happening on the expedition itself. So what is the support you're getting on the expedition? Now the first thing I want to look at is physical support. So this is going back to my earlier statement. If you're going on a hike with a bunch of friends and you have one friend who's like, yes, I will carry all your packs for you. Don't worry, you can just walk by yourself. You would expect that your own energy expenditure would be a lot lower. And that is exactly what we're finding. So the question that we specifically asked was, how many people can you depend on for physical support? And if they said that they could depend on more people for physical support, they had to spend less energy overall. So they were able to share the load, physically, literally share the load. But things get a little bit more interesting when you're thinking about emotional support. So now you're not asking someone to carry your pack for you. Now you're not asking someone to help you set up camp. Instead, you're like, I'm really stressed out, I'm really sad, I don't really know how I'm going to get through the rest of this course, but how many people are you able to confide in? How many people are you able to seek support from emotionally? And what we find is that this follows the same pattern, where individuals that have greater emotional support have lower overall energy expenditure. So there's something happening physiologically about getting social support, about having a group that allows you to be more conservative with your energy usage. And now the big topic in the space industry, in aerospace, in any sort of extreme environment, you talk to the military, etc., what everyone wants to know is resilience. You know, we're looking at, okay, great, social support is great, whatever, but resilience, how do we make sure that people stay resilient? So the question we asked was like, how resilient do you feel throughout the entire process? We asked them a series of questions to get this resilience score and wanted to see how it mapped across these physiological changes. And it seems that it maps exactly the same as social support. So individuals that felt that they were more resilient had lower overall energy expenditure. So now what are some of the takeaways that we should take from this specific data set? Now, one is that the research considers this relationship between multiple physiological and behavioral systems. From the earlier factor map, we can see that NASA has lots of concerns, many, many, many concerns. But in repeated conversations with many of the head scientists, the biggest issues come from what we don't know. Now, what we don't know is most likely going to come from the intersection of different systems. We have lots of researchers that are working on just the cardiovascular system, just the immune system, just behavioral systems. But what we need to be looking at is the intersection of all of these systems together. Now, the second thing is that we're seeing that both environmental context and interpersonal relationships impact physiological function. So when we're thinking about putting someone on a long-duration mission, we can't just think of what physical environment that they're in. We also need to consider the group dynamics, the social components as well. And so this data specifically is showing that the social support from home and both physical and emotional support from the expedition itself, and as well as self-reported resilience, are all related to this lower energy expenditure. Now, when you're thinking about how much resources you have room for, how much energy any crew member needs, these are all things that we need to be considering. Okay, so now when we're thinking about long-duration spaceflight or extended habitation on Mars, we have a couple of things that we need to consider. First, it's that humans are flexible, plastic, and adaptable. The changes that we undergo in any environment are likely our body's attempts to actually keep us going. Even things that seem like they are making us more unhealthy, they are close adaptations to what is happening to the environment itself. So we need to just decide if it's something that we can work with or not. The next is that we need each other to survive, both from a pragmatic standpoint, but also from how humans have evolved. We're seeing that these systems are very, very closely linked with each other, and we depend on social groups and support, and it is impossible to look at individual physiology without also looking at the larger group. And the last thing is that there is so much we don't know. In fact, just 5 years ago, doing a project like this would have been unthinkable. Why are you even bothering to look at these different systems together? But what we need is we need not just scientists and engineers, but physicians and artists and historians and lawyers and policymakers, even more to get an inkling of what we're stepping into. As we start to venture from not being just a spacefaring species, but an interplanetary and perhaps even an intergalaxy species, we need to know that nothing is possible without the shared knowledge of all of humanity working together. So the whole pitch of my whole thing is that it takes a village. So I'd like to thank my whole research team. I have really amazing collaborators, Shannon and Sarah from Knowles, Lee Gettler and Kara Akbach from Notre Dame, and my really wonderful undergrads, Clarissa, Veronica, and Jane, as well as my funding sources. This work is expensive, and so thank you so much to my many funding sources. And I want to leave you with this great photo of social group dynamics and camaraderie among the ISS astronauts that happened just this Thursday over Thanksgiving. Thank you so much.
Thank you so much for your talk. Whenever we have space people here, it's like my favorite days, so thank you. So my question is, you briefly mentioned the idea of celestial dust.
Yes.
What is that? How much should we care about it? Like, why would it possibly impact us?
Mm-hmm.
You know?
That is a very good question. So I think that celestial dust takes care of a whole bunch of different kinds of dust. So not just dust in, a space, but also anything coming off of any planets, any celestial bodies. So for example, the moon. The dust on the moon is extremely, extremely harsh. So if we were to keep a piece of, some just equipment on the moon, we'd have to make sure that it's relatively hardy, because just the erosion that would come from the dust would basically destroy it. And the dust on Mars is completely different from the dust on the moon. And so there are a whole bunch of geologists, people that specifically work on dust particles, that are trying to figure this out and figure out what exactly does it mean for equipment. Now, what it means for the human body, no one has any idea. Unfortunately, the Institutional Review Board ethics committees won't let you take a human and just throw a bunch of dust at them. It's very unethical. Don't do it. Bad idea. I don't actually even think that there are any mouse models or rat models that they're looking at this kind of things for. But for your question about how it could possibly impact us, so we know that dust particles here on Earth impacts people in so many different ways. Anyone here has asthma? I know tons of people with asthma. That's just Earth dust particles that are getting into your system and causing all sorts of issues for your pulmonary system. Now, what that might happen if you say that your lungs are working fine, but you're swallowing this dust and there might be something in it that is messing up with your blood, if it's messing with your GI tract, we honestly have no idea. So that's something that we are trying to figure out right now. Great question, though. Do I choose? Okay.
I wondered if you could talk a little bit more about resilience. It's so much of interest for so many spheres of life right now. I wonder if you could talk a little bit more about how you broke it down into its various components,
yes,
how you developed your questions, how you tested those questions, just if you could dig into that a little more.
Absolutely. So this is actually something that I have thought very long and hard about in both my fields of my background in psychology as well as anthropology and biology. Resilience is thought of in really different ways. And then you take that into an operational sphere and it's thought of completely differently. So for this specific project, resilience was a validated questionnaire, so thinking about psychological resilience, but questions that we asked were, how well do you think you bounce back from something bad that happened? How do you feel that you responded to this bad thing well? And so it was very specific to acute resilience. So if something bad happened, can you respond from it? Can you react from it? Now, there are much larger questions thinking about biological resilience. So, even if we're seeing major shifts, major changes that are happening, is that actually a resiliency factor? Is that a good thing that we're seeing these changes? It's not something we should be concerned about. It means that your body is adapting and is resilient to that environment. That's a conversation that I am having. That is a conversation that a lot of my colleagues are having, trying to come up with either a unified definition of resilience or something that works for everyone. But you asked a great question because we are still trying to figure that out. But for this specifically, it was looking at acute resilience, what is happening back and forth. My hope is that in the future, because I have all of these physiological measures looking at all the hormone levels and energy expenditure measures and even immune factor levels, if I can create somehow a physiological profile, so like in this environment, they're experiencing all these really hard, difficult things, and these people are doing better, these people are doing worse. Are we considering these people to be more resilient or not? Check it against their own self-resiliency scores and see what happens.
Is anyone in your field studying popularity?
Popularity. So I'm not sure off the top of my head, but I know that there are a whole bunch of teamwork scientists, actually some at Northwestern, so really close to here, and some at Johnson Space Center that are looking at team dynamics on extended missions, both in space but also like in Antarctic winter overs, etc. And I think that one of the things that they are collecting is how popular individuals are. So I can talk a little bit about, this is like just recently analyzed like a couple days ago, so I'm saying this with many, many grains of salt because I need to make sure that the math I've done is all correct. But some of the data that I found with my work is that there is a difference between people who, like if lots of people can depend on them, then they actually have slightly different physiological profiles than people who are like, oh, I can depend on lots of people, but no one can depend on me. I am the freeloader, I get help from everyone, but I don't give any help to anyone else. Whereas people that are like, okay, I am here to help everyone, they are still being able to get help from other people, but they have a cost for helping other people. So it kind of addresses this issue of popularity. Does popularity have a higher cost because you are now the center? Okay, this is going off on a little bit of a tangent, but there is really excellent work by Robert Sapolsky. He's out of Stanford on baboons. So a lot of actually my inspiration for doing this social work comes from that research. And it talks, so baboons, like humans, are highly, highly social. There's a lot of grooming, there's a lot of group activity involved, but they are also extremely hierarchical. And what we find is that individuals that are alphas, that are in the center, that are the leaders of the group, so arguably the most popular, they tend to have really bad physiological profiles. They're like sick all the time, and like they just need one push and then they're off. They're no longer on top. And it's the stress of being in charge, the stress of being popular, but you also see it's kind of this U-shaped curve. On the other end, if you're super isolated and no one likes you and you have no friends, you also have a really terrible physiological profile. So there's this kind of U-shaped curve. You know, sometimes it's okay to be like second rung, third rung, because you don't have the stress of being in charge, but you still have friends, so you're not totally isolated either.
Sort of along the same lines. Have you looked at adverse childhood events for participants in the groups?
So are you specifically asking about like if they experience a specific traumatic event, like a avalanche or something like that?
Well, I've read that adverse childhood events are things like emotional trauma,
childhood events, yes.
Sexual abuse, et cetera, and those things now are understood to predict adverse health outcomes later in life. So I wonder if they might also be relevant to what you're doing.
That is an excellent question. So for this particular study, we did not look at kind of early childhood early life experiences. Actually, a lot of work that I did before starting this research was looking at that same thing. Like whatever happened to you as a kid, whatever happened to you as a baby, even as you're growing up your developmental period, how is that impacting your later on physiology? And you're absolutely right. It does have huge impacts on how you function. And I think that the future of this research is looking at these two things combined. So getting this whole history of what's happening to an individual before they are even starting, and then looking at what's happening while they're actually on the course or on a mission or whatever itself. But they definitely do interact with each other. In fact, there's a lot of research that shows that depending on what happened early on in your life, it can determine kind of the range of adaptation that you have later on. So if you had a particular lifestyle, if you were encouraged as a kid, you had all of the nutritional availability you needed, if you had all the support that you needed, then when you are facing a really highly challenging environment, later on, you are able to respond to it better. You're able to respond to it more accurately. And the closest I really get to in my study specifically is looking at that from home social support, but it doesn't really capture everything we'd like. If I can convince government agencies and independent funding agencies to give me lots of money, that is definitely something I'd be looking at in the future.
Right here.
Hey, so thank you for that. I had a question about some of your results.
Yes.
So you plotted and it showed this negative relationship between, let's say, energy expenditure and the other social factors.
Right.
So it's like, is it a linear relationship, or does that have some sort of maximum, right? Like if you have 100 people that you're relying on, are you going to have negative energy expenditure? Like that's sort of my thought. So what's the limit on that? And then like what's the upper end of that?
So these data are limited by size, like the N value. I mean, for a human-based study, it is a very high end because it's around 71 individuals. Most human-based studies are like 15, like less than that. But because like an N of 70 is still an N of 70. And so for doing the actual statistics, we can't actually extrapolate what the upper and lower limits are, but I think theoretically we can. So if you're depending on 100 people, for example, are you actually depending on 100 people? Is that an actual measure? Is that something you can say that is a reliable measure in any way? Probably not. I think that, like, just from my own conjecture, I think that's probably not any help at all. In fact, we have a couple of, this is something that I'm trying to tease out in my own data, is that there are a couple of people that when they're asked to list who are the people, list the names of the people that you can depend on, and some people just say all. So like the people who are just saying all are not even bothering to list everyone. Does that mean that they are actually depending on everyone? Probably not. Like if you are ever in a team group, if you're in a work activity, you're like, all of my coworkers are awesome. Are they? Are they really? Probably not. So that is a really great question. I think also the lower limit, so if they're saying, I depend on no one, I think that is something that, like, hopefully in the future, if there's tons and tons of data, to kind of parse that out, because I think that that's when things like personality kinds of pushes things either way. So if you have someone who is, like, extremely independent and is really, really uncomfortable around people, maybe having no social support, maybe feeling that they don't have to depend on anyone is a slightly different profile. We don't know that yet. So that's the wonders and fun of human data. It's like a sandstorm, and you kind of see a pattern, and you're like, okay, theoretically, does this make sense? Does this not make sense? But we just hope for more and more and more data. So eventually, a clearer pattern will hopefully emerge. But great question.
What do we know about the data that was collected from the twin astronaut that spent time in space?
Great question. So there has been an extensive review that was just published this past year in Science, actually, that has a compendium of all of the different things that they looked at for the twin study. So those of you who aren't familiar with the twin study, Scott Kelly, right here on the left, went to space for just under a year. So he was the first American astronaut to have gone into space for that duration of time, and had like the extended period without interruption. The Russians have been doing this for a very long time, but there's a lot of politics, a lot of drama. The Russians won't necessarily share all their data with this in full, so the US decided to run their own study. Now, luckily, Scott Kelly has a twin brother, identical twin brother, who is also an astronaut, right there on the right. And so there are a lot of ethical IRB problems about collecting this kind of personal data. So actually NASA hadn't intended on collecting any of it at all. In fact, they were all sitting down together and they were getting Scott ready, and they were like, okay, these are all the studies you're going to do. And he's like, wait, you guys know I have a twin, right? Don't you want to collect like genetic data or more intensive data on both of us? And they were like, wait, can we do that? And he's like, we'll find out. Let's write a proposal, see what happens. And it turns out it worked out fine, and they got approval to do stuff. Lots of paperwork, but they got approval to do stuff. So I would strongly encourage, if anyone is interested, you can email me or you can find it on the internet. It's on Science. It is all of the various studies that they've done. So some of the things that really stand out here is They collected, I think, telomere length, immune system function, cardiovascular systems, genetics, epigenetics, so just like their genetic code, but then also the changes that were happening to their genetics during that time. They had to undergo multiple spinal taps. I can't imagine that it was fun at all. But some of the things of note that stand out were that Scott Kelly came back and his telomeres were longer, and no one really knew what was going on. In fact, the PI that was in charge of that project, I talked to her a couple months ago, and I asked her, do you have any idea why this is the case? And she's like, nope. They're still trying to figure that out. And do telomeres tell us the same things that we think they do? So telomeres are the little wrappers, like the shoelace ends on the end of your chromosomes. And as you get older, they kind of degrade and deteriorate. But what was happening is they were stretching in space. And when he came back, it's okay, are they returning to normal? Kind of, not really. So a lot of it is okay, we have no idea what's going on. We obviously require a lot more research. But it also is really cool because it completely changes what we know here on Earth. We're oh, telomeres are just always attached to old age. But it's is it though? Is it actually attached to old age? And then some of the other stuff, I think they're still in the works of trying to figure it out. I know there was some interesting microbiome data. I don't know what the findings were off the top of my head, but and I think immune system function was altered. The cytokines were actually different, but I think it returned back to normal. One other thing was his vision. So this happens with lots of different astronauts when they go up into space. Oh, I actually have another fun thing about this. So when you're in space, your fluid shifts change. When you're here on Earth, you have gravity. Gravity is wonderful. It pushes all of the fluid down to your body. You don't have to do a thing. So all your body really needs to do, your heart is pumping, is just pushing things back up. But when you're in space, that doesn't work like that because you have nothing that is pulling all of that down, and so everything just kind of gets stuck up here. So if you go back to this photo of the astronauts, you can see, so if you look at this and you compare them to pictures of them on Earth, their faces are way puffier. They look kind of bloated. They look like, they desperately need some electrolytes. And they tend to have chicken leg syndrome, where they have big puffy bodies and then really, really skinny legs. And it's because all the fluid shift is up there. Now, fluid shifts are all fine and good, except that your fluid is also going into your brain, which is not good when you have too much of it, because this is what happens to your eyeballs. Yeah. It's very scary and weird. And this is something they're still trying to figure out, what the heck to do. So with Scott, they're not seeing this kind of extreme level of compression with his eyeballs, but he did have some vision changes, but they seem to return to normal. For some people, it returns to normal. Other people just have terrible vision for the rest of their lives. So thinking about going into space, that's something that to consider.
This is kind of a double-barreled question. From time to time, news items appear about people who have signed up to colonize Mars in the knowledge that under the current state of the art anyway, they most likely could never return.
Yes.
Has there been any scientific observation of the questions? Number one, what would motivate somebody to essentially acquiesce in what could be considered a form of civil death?
Right.
And number two, as a practical matter, how would it impact things like inheritance, life insurance, et al.?
That's a really interesting question. And I think probably why we need to go back to why we need to have policy folks and lawyers. I'm definitely not a lawyer, so I feel like I shouldn't be giving any input about how inheritance laws and stuff would work. But I do think it's interesting from a psychological perspective, for example. So why people would choose to go on a mission like this. So I think there is a long history of humans in general putting themselves in really, really dangerous positions because they can. If you're thinking about Shackleton's expedition to Antarctica, you had the ad in the newspaper was, Like, it's not going to be fun and certain death, and just come if you want to. People signed up. People really wanted to do it. And if you think about the Mount Everest expeditions, people trying to even now, people trying to climb Everest, you hear stories about the amounts of, like, people are just climbing over bodies because it's so dangerous and the infrastructure is deteriorating because of so many people. I think that humans are always going to go somewhere because they can. Now, if that's actually a good thing, if that's something they should do, that becomes really questionable. And then I think that there's a whole other conversation, this is the anthropologist in me coming out, about how we think about human expansion, how we think about future human habitation. I personally try to take colonization out of the vocabulary, because colonization has a long and horrible, horrible history. It has a lot of baggage attached. And when we're thinking about something as amazing and incredible as human habitation on a different planet, do we really want to carry the baggage that colonization brings? And so, again, that's why we need people who are in the liberal arts who can have these conversations along with the scientists as well. And so, depending on how we think about human habitation, it determines things like policy. So if you are living somewhere, if you're living on Mars, if you're living on the moon, if you're living on a shuttle, if you're living on the shuttle, does that count that your residency is on the shuttle, or is it like you're just on a trip somewhere? Where do you pay taxes? You know, these are great questions. I don't think I'm the most qualified to answer them, but I definitely think that they are worth asking.
I was wondering what effect exercise has when you're in space, because the gravity is different. Does it have the same effect that it has on Earth? What is the effect of it?
I love that you asked that question. I just realized I thought I had added in a couple of videos about that, but I didn't. But I'll just tell you about them instead. Okay, so who here has heard about when you're in space, you lose bone mass and you lose muscle mass? Okay, so nearly everyone has heard that.
Bone density.
Yes, bone density and muscle mass. And so that was the case when we were first sending astronauts up into ISS. Now, that wasn't really an issue for Apollo missions, Mercury missions, even shuttle missions. People are not really in space for that long to have these dramatic changes. But ISS, people are staying there for extended periods of time. When you have gravity, part of what it does that it works on, you are doing exercise itself, just getting out of bed. So if someone gives you a hard time about not going to the gym, if your New Year's resolution is like, I need to go to the gym, not really. I mean, you're just getting up, and that's exercise itself because you live here on Earth. Now, when they first were on the ISS, they were realizing that people were losing dramatic bone density and muscle mass. And that's because you don't have gravity pulling down on you. So they implemented a whole series of exercise regimes to try and combat that. And now, that is actually not the case. We actually have countermeasures in place, so our current astronauts are not losing bone density and they are not losing muscle mass. Now, the trick is that a treadmill, they thought that, okay, if we're just doing aerobic exercise, that's fine. A treadmill is not actually, it doesn't really work. You have to do a treadmill plus high-intensity resistance exercise. So they have this thing called the Hulk. It's very cool. I recommend looking it up. It is like a machine you strap yourself into, and it's like a bunch of straps, and you basically are like bench pressing and back squatting, but it's short, resistive exercise motions. Now, a lot of the osteoporosis work that's done here on Earth, looking at elderly women, has really, really benefited from the space community because it's the same kind of loss in muscle, loss in bone density. And so it's really turning the medical community on its head because you never want to tell a osteoporotic woman, oh, go do heavy weights at the gym. That seems really, really counterintuitive. But at least what we're seeing in the space research is like maybe, high intensity resistance exercise is the way to go. But yes, exercise, it makes a big difference.
Two topics that popped into my mind were Wi-Fi and sex.
Yes. Those are great topics, and I think they are on, when people are trying to come up with these missions, people don't want to think about them, but they are things that need to be considered. So Wi-Fi is something that on the ISS is not a problem at all. We don't have to worry about that. There is like a slight communication delay, but astronauts can get Wi-Fi when they need it. If they need to look something up, they want to Wikipedia something, they are watching a movie and want to look up who the actors are, they can do that. That's not an issue. That becomes a big issue when you are going to the moon, when you're going to Mars. All of these systems, internet systems, etc., are based on home Earth networks. The farther away you get from Earth, the harder it becomes. So there is a lot of work that is being done on AI and kind of self-reliance systems. So things that are like medical emergencies, how can astronauts solve medical emergencies without having access to the internet, without having access to experts, without being able to read their email, etc. But also, you can't talk to your family, which is hard. So if anyone here has been on an extended camping trip, or like I do a lot of field work, so I was like in Congo for 2 months, and the only way to talk to my family was to call them on a sat phone, which is extremely expensive and usually only reserved for emergencies. But it was really hard. And it's not like you can write letters or you can text people. Like that's like not possible. So using AI systems is if you can have an AI system that looks like your mom, and you can just talk to your mom robot and cry to her on the phone because some crew member is being mean to you. Like, does that actually help your psychological well-being? Maybe. That's something people are actually looking into. Now, the sex question is really, it's really interesting because no one really talks about it in the ways that we should talk about it. Sex is a part of social behavior just as much as everything else. So we shouldn't just be talking about it from a purely physiological standpoint. And there is a lot of research on that. There is a whole group of researchers that is doing work on pregnancy in space. Is it viable? Is it possible? Is it something we need to think about? Right now, it has never happened, and it is not something we want to think about. The levels of radiation exposure is extremely high. The levels of stress that people get just from transit, not necessarily being in a weightlessness or spaceflight environment, that is going to impact the fetus. There's a whole field of high-altitude medicine. So they're not really in extreme hypoxia when they're in the space station, but the conditions are still different. But what we're seeing in hypoxia medicine is that high-altitude pregnancies are different. So you have populations that are adapted to high-altitude pregnancies, so Tibetan populations, etc. But you have populations like the Han Chinese. If they're moving into highland Tibet, they can't keep a pregnancy. They have to go back down so they can gestate and deliver a viable pregnancy before going back up. So that is a whole thing by itself. But the social questions about sex in space is really important. I don't think is understood very well. From the various memoirs of astronauts, etc., I feel like it's probably happened, but no one talks about it. And right now, I can't really speak for the other countries, but US astronauts are kept to an extremely tight schedule. So they have their schedule, and they actually have, I learned this recently, they have like a red line that is like constantly moving down. And so you are always trying to beat the red line to make sure you get all your tasks done. So I feel like that's probably not the kind of environment that is, that would promote wanting to have sex, but I don't know, maybe. But definitely something that we don't know that much about.
If we wanted a roadmap to figuring out how close we are to getting to Mars, what would be the 2 or 3 milestones that would tell us, we're far along, we're almost there, and so on?
That's a great question and a slightly political question. So the roadmap to Mars exists, okay, but it changes often based on who is in power politically across the world, but also like the discoveries that we make, etc. The current goal is that we would be on Mars in the 2030s, the mid-2030s. The recent administration has shifted priorities to moon, to use the moon as a proving ground, as kind of like an extended laboratory to test equipment, etc., and then go to Mars. But that's just the U.S. So we have many agencies. And I think that it's like the large majority of countries in the world have a space agency. Now, like the level of intensity that they're at, the level of viability that they're at is very different. But I think that given the funding and kind of the historical preferences. I think probably like the US, ESA, JAXA. So ESA is a European Space Agency, JAXA is Japanese Space Agency. They have a very, very strong relationship with each other. And Canadian Space Agency, the four of them together. They are probably, they're gunning for the 2030s. Now China is doing kind of its own thing. They've already landed on the dark side of the moon. They planted a plant on that side. It was a big deal. They are probably aiming for around the same point. Now that is kind of like an administrative perspective. So the big questions right now is engineering. If we kind of threw in all of the money that we had, we're like, we have to get to Mars by 2030. Engineering is not an issue. The questions that they have about engineering really couldn't be solved by like really intensive time and money. And I don't think that would be a major problem. The biggest issue, and this is something that even engineers say, and it's like pulling teeth getting it out of them, but the biggest issue is like what's going to happen to a human. Like we can send rovers, we can send robots to Mars, no problem, but we have no guarantee that we can keep humans alive for the length of time it's going to take both to get on Mars, stay on Mars long enough to get enough good data, and come back. So I would say that, you know, the thing that we need to be looking for is as soon as we can figure out how to keep a human alive and well in space / an extraterrestrial environment for around 3 years, we're going to be good to go.
What about the question of food? What will we eat up there, especially for an extended period of time? Do you think there would be much use of hydroponics?
So I think that there's a lot of conversation about food and what we need to do. So in the early days of the space industry, I'm sure that like when I was a kid, I went to Johnson Space Center and we could have astronaut food. It was freeze-dried. It was horrible. But it was easy to pack, and it was small, and it had nutrition, maybe? I'm not actually sure. But people don't like to eat that. And the thing is, a lot of times you find out that if people don't like to eat food, they just won't eat it. And that is not good if you're sending someone out on an extended mission. They have bone muscle mass loss because of gravitational changes. They're feeling really stressed out because they have to talk to their robot mom instead of their actual mom. So there are all of these things happening, and we all know that food has a really, really important role in our lives and our well-being. It's not just nutrition, it makes us feel good. So the past couple of years, like in the past 5-10 years, they've been trying to do self-sustainable farming on ISS. So they grew lettuce, they grew zinnias. Turns out that lettuce was a terrible thing to grow. The FDA came by and we were like, why are you growing lettuce? You know, that's like the easiest thing to become contaminated out of all grown foods ever. And they were like, oh, really? What? I had no idea. The importance of why interagency communication needs to be there. But so there is an importance in growing actual foods, like you've grown yourself, like real vegetables, real fruits, even seeing actual flowers. I think that probably the first couple missions that they sent to Mars, this is just my own conjecture, so I'm not speaking for anyone or anything, this is what I'm thinking, they'll probably have to do something that is like extreme protein packs or extreme carbohydrate packs that are like, you know, pellets or whatever, and then they'll supplement it with like actual lettuce or like potatoes or something like that. They probably, but like for now, they're going to try and keep everything as nutrient-packed as possible. They probably won't taste very good, but they'll be there. The people that are likely going on these trips, I feel like probably say they don't care. They're like, I'll eat whatever. As long as I can go to Mars, they will care. By year 3 on their way home, they're like, please, I just want regular food. So there's actually a whole group of scientists that's their job. They're trying to figure out how to grow plants, how to like keep food, you know, processed food viable, etc., for long periods of time.
I have a question for you about sort of race, gender, ethnicity. So yes. We know from medical research and health sciences that a lot of the things we consider to be like the norm, it's based on a very small subset of white men of a certain age.
Yep.
So I recognize with a group of 70, you probably can't cross-tab by all these various features, but I'm just wondering what research is out there, or what research do you wish would be out there, sort of looking at, race, ethnicity, gender, age, those kinds of things?
That is fantastic. As an anthropologist, this is something that hits at my core all the time. It's like the first thing that I look at. Usually the first time I look at studies, I'm like, where are they looking at all these different things? For my study, I actually look at gender, and I'm looking at the differences in gender. It was interesting because in an earlier study done on the same population, there were gender differences. But in my study, there aren't gender differences. And I think that the reason why there for that may be because the population that was done like 5 years ago was in a much worse physiological condition early on. So like they had extremely low fat stores even before starting their expeditions. They were like very, very, they had very, very low fat. And that like, the whole thing about like diet cultures and stuff like that. Fat is good. You want to actually have body fat, especially when you're doing something really intense like this. They're literal pockets of energy stores. It's like we're all squirrels with seeds in our pockets, but their seeds are our tummies, and they keep us going through the hard times. But like the earlier group didn't actually have very high energy stores, and so I think that's probably why this group is like healthier, more robust, and so we're not actually seeing those very dramatic gender differences. Now, race is really hard. There's this group, there was diversity in ethnicity, but not nearly as much as necessary. And the reason is because if you're going on this course, it means that you're in the socioeconomic status that you can afford to go on this course. Now, we had students that were able to come on like major scholarships, but that's not nearly enough, which is extremely frustrating. Now, especially connecting it back to space research. So the very earliest research that was done is on like the Mercury 7, like the Friendship 7 astronauts. They're all like extremely hyped up, type A personality, a flight tester, white dudes. And they're all of a very similar personality, they're all of a very similar build. And that's what all space research was based on for a really, really long time. And so even things that we're seeing about differences between males and females, understanding reproduction in space, understanding how nutrition changes in space, we don't even know even a quarter of it because all of the research has been done on such a small group of people. Now, some of my earlier work, because this is something that's really important to me, is I've been looking at populations around the world that are adapted to different kinds of extreme environments. And what we see is that there is an immense amount of diversity, but also adaptability in different populations. And a lot of it has to do with what the one gentleman said earlier about your early experiences. So like if you're looking at high altitude populations, if you're in a population like a Tibetan population, for example, your entire family generations have been living at high altitude, your body is functioning literally differently at high altitude. Now, what happens if we take someone like that and we send them to space? We have no idea. And that becomes a social-political issue, an economic issue. Who has access to space? Who has access to these extreme environments? And that is something I feel really, really strongly about. I think that there is a pitiful amount of research done given the overall diversity of the human species. We don't know nearly enough, and a lot of it, I think, is driven, unfortunately, by, this is good enough. If we look at, cardiovascular disease in a bunch of white men, that covers everyone, and it doesn't. It really doesn't. And we're only kind of noticing that recently, and so I'm hoping that the tides will change.
Why space versus Earth? Not to disparage space research, but when I hear of space research, I often think our Earth has so many problems. Why is there not more focus on solving, like you're talking about the outdoor leadership program. Mm-hmm. They're hooked up with all of these monitors to measure. People who live in West Chicago.
Yeah.
Research like that done to say, okay, what's going on with these people because of their environment? How could it be improved? I know politics gets into it. I know some topics are more sexy than others, and the funding's there. I just wondered what your opinion was.
Yeah, thank you so much for asking that. And I, as someone who is a early scientist, an early career scientist, it's something that I think about all the time. Am I spending my time and my resources doing what I should be doing, or should I be working on something else? Now, I think that I agree. There are many, many problems here on Earth that need to be solved. I think that when I see people talking about space as the answer, like we're just going to leave Earth and just figure out space and not even worry about things, I think that's a really silly way to looking at it. Because in the end, humans, whereas a species, we are, no matter if we're on Earth, we're in space, we're on Mars, wherever, we are still going to have the same issues that we have to deal with. The environment is going to be different, the stressors are going to be different, but we still have the same issues. So ignoring it on Earth isn't going to make things better. Ignoring inequality on Earth isn't going to make Mars an automatic utopia. That's not how it works. Now, as to why I choose to study space, I think that there is a lot of value in looking at what is happening to come, like what can happen in the future. I am very honored and happy that a lot of my colleagues are working on things like, minority populations or underserved populations in urban environments, or for example, even where I was working at Knowles, looking at indigenous populations, like they've been in really, really bad conditions due to a lot of social political pressures, and how can we better help those kinds of communities, et cetera. And I think that for me, being able to be in the future and kind of make sure that these same considerations about diversity and equity and making sure that we minimize inequality and access to everyone, if I can do that in science that is looking forward, then I'm happy to be playing my part. I think another thing is that, this is oftentimes an argument against doing human spaceflight. Why? Why even bother? It's so much easier, it's so much cheaper to send like robots, to send rovers or satellites, etc. Like, why are we even bothering? But I think it's, again, humans do it because they can. And we might as well have people who are thinking about these things, asking those questions, as opposed to people who just want to go and like capitalize on them, for example. So, and I think that like things that we're learning here in space research, whether it be the osteoporosis work, or we're learning about fluid shifts, which is going to be relevant to patients that are in extended bed rest, because you're having similar kinds of fluid shifts. These are all translational research items. So for me, all of the research that I do, I want to make sure that it is translational. It doesn't just have spaceflight applications, but it does have applications here on Earth as well. And again, I can't speak for everyone, but that at least is my own personal motivation.
Okay, we have time for one last question.
I'm wondering what they're thinking about for housing. I was recently looking at some articles and YouTube videos about 3D printed houses. There was this elongated beehive that was about 7 stories tall that had hydroponic gardens and all kinds of things that you've been addressing. But I just laughed because the equipment needed to build a 3D printed 7-story is a bit more massive than the spacecraft itself, probably. Yeah. Plus, then where do they were going to use the dust to make the materials, but you still need some kind of liquid binding thing.
Exactly. So I actually don't know too much about what is happening with the housing situation and how they're going to try and figure it out. But I think that it reaffirms my commitment as to like why you can't just have engineers and scientists doing everything, and you really need architects, you need artists, you need people who are able to kind of think about these different problems and create interdisciplinary groups to kind of come up with solutions. So like maybe our solution is to have some sort of beehive-like housing with 3D printers, and like you need like a chemist to come up with like a new kind of material based on what's available. But what we need these interdisciplinary groups to actually think about these things. So I'm sorry I can't really answer your question. I don't really know too much about the housing, but I think it is an important question.
Thank you, Mallika. That was terrific.
Thank you.